All right, today we're diving into a really radical idea. What if we've been thinking about the fabric of our universe all wrong? We're talking about expansion, pre-stress, and the thermal history of spacetime. So let's just jump right in with a question that's kind of mind-bending. What if? What if cosmic expansion and black holes aren't these two separate, giant mysteries we've been chasing? What if they're actually just two sides of the same coin? Opposite states of some hidden structure in spacetime itself? To even begin to answer that, we've got to peel back the layers. This model suggests there's something hiding right under our noses, beneath everything we see, a hidden structure within spacetime. Okay, so the core idea here, it pretty much challenges everything. Forget thinking of spacetime as just an empty background, like a stage for the universe to play on. In this view, spacetime is the play. It's a dynamic, elastic lattice. And that means it has real physical properties. It can be stretched, it can be squeezed, it can be warped. And here it is. This is the proposed fundamental building block of that whole lattice. It's a dual tetrahedral unit called an cell. Now, think about this. This isn't just a pixel of space. It's meant to be the fundamental atom of reality. It completely throws out the old idea of a smooth, continuous spacetime and replaces it with this discrete, geometric structure. So, okay, if spacetime is a physical thing made of these little cells, how does it actually work? Let's get into the rules of this elastic reality. All right, rule number 1 is all about size. Imagine each one of these cells has its own natural size, right? Its internal scale. And this scale can change depending on what's going on around it, how much it's being stretched or squeezed. And here's the kicker. When the size of these individual cells changes, the entire lattice expands or contracts with them. It's a really simple idea, but it's basically the engine for everything else we're going to talk about. So you've really got two basic states here. On one hand, you have expansion. The cells get bigger, the whole lattice opens up, and, this is super important, it gets softer. On the other hand, you've got compression. The cells are squeezed tight, the lattice gets way denser, and spacetime becomes stiffer. And I want to be clear, this isn't just a metaphor. We're talking about a real physical change to the fabric of reality. And this connection between size and stiffness, it isn't random. It's governed by a very specific rule called the universal scaling law. And what it tells us is that a bigger lattice is a way softer lattice. And that's not just a neat observation. It's proposed as a fundamental law of physics in this model. But wait, it gets deeper. The lattice isn't just sitting there, waiting for things to happen to it. This model introduces something called prestress. Think of it like a built-in background tension that's just always there. This global tension basically sets the universe's master clock. And there's also a torsional bias. You can picture it as a tiny universal twist in the fabric. And that's what gives time its arrow, its forward direction. So get this, time itself isn't fundamental. It actually emerges from the physical state of the lattice. Okay, so we've got the rules for our elastic spacetime. Now for the big test. Let's apply them to the biggest observation in cosmology, the expansion of the universe. And the answer this framework gives is, it's incredibly elegant. Expansion is just cooling. Check out this chain reaction. It's wild. It all kicks off with spacetime itself cooling down. As it cools, that background tension we talked about, the prestress, it just relaxes. And that lets all the individual cells kind of puff up and expand. And when you have trillions and trillions of these cells all expanding at once, the whole universe grows. It's just thermodynamics, but playing out on the grandest scale imaginable. So the real takeaway here is this. An expanding universe is also a softening spacetime lattice. Remember that scaling law we mentioned? As the universe gets bigger, the very fabric of spacetime literally becomes less stiff. It's a direct physical consequence. One causes the other. All right, so let's flip the script. If expansion is space-time relaxing and getting softer, what happens when you go to the complete opposite extreme? Well, that's where black holes come in, and this model sees them as the ultimate state of compression. What's so cool about this is that you don't need a whole new set of physics to explain black holes. They're just the other end of the spectrum. They are the absolute maximum compression and stiffening of the space-time lattice. Not some weird separate thing, but the literal inverse of cosmic expansion. And this gives us a totally new way to think about the event horizon. The idea is that at the horizon, the lattice itself doesn't just vanish. What disappears is our ability to see it. It becomes so incredibly compressed, so stiff, that it basically can't communicate with the outside universe anymore. Its properties can't project outwards. And you know what else this explains? Hawking radiation. Suddenly, it's not some mysterious quantum effect that's happening on top of spacetime. No, it's a direct result of spacetime's geometry. That incredibly sharp change in stiffness right at the edge of the horizon, that's what produces the thermal signature. It's a physical boundary effect, plain and simple. Okay, so we've got expansion as space-time cooling and relaxing, and we've got black holes as space-time being compressed to its absolute limits. Now let's pull the camera way, way back and see what this new perspective tells us about the entire history of our universe. This paints a pretty staggering new picture of the beginning, doesn't it? Forget the idea of a singularity, an infinitely dense point that doesn't make physical sense. Imagine this instead. The early universe was a real, physical thing, an ultra-compressed, unbelievably hot, and incredibly stiff state of the space-time lattice itself. So we can rewrite our whole cosmic story. It doesn't start with a bang from nothing. It starts with this primordial state of maximum compression and heat. Then, that state begins to relax and cool down, which causes the lattice to expand. And that process leads us right to where we are today, in a universe that's still expanding and getting softer. In this view, cosmic history is the thermal history of space-time. So let's boil it all down. What's the big picture here? 1. Space-time isn't empty. It has a hidden elastic structure. 2. Cosmic expansion is just that structure cooling down and relaxing. 3. Black holes are the total opposite, extreme compression. And 4, even something as fundamental as time emerges from the background state of this lattice. And that leaves us with one last, kind of awe-inspiring question to chew on. Is the entire universe that we see, all the galaxies, all the stars, all the black holes, is it all just the visible story of space-time itself, changing its own internal state? A reality where the stage and the actor are one and the same? It's a lot to think about.